And moving on to the next page, which is the next kind of thing that we're going to do. So we just got done talking about confidence intervals. This next type of problem is a test of significance. So whenever they talk about a percentage, they're talking about a confidence interval, and everything else is called a test of significance. Why? Because that's how they choose to talk about them. So when they talk about a test of significance, you're not doing the 95%, 90% thing. When they talk about confidence interval, you are. So in this one, process is very similar as usual. You're going to state the null hypothesis and the alternative hypothesis. We just spent a few days doing this in chapter 9. Except this time, you're going to take the difference. You're going to subtract those two proportions. And then you're going to define your P1 and P2 just like we just did. Our planning stage, we're going to say we're going to do a two-sample Z test, not confidence interval, test, for P1 minus P2 or P10 minus P9 or whatever we call them. In our conditions, we say that it's random. For normalness, we do the NP thing again. Independence, population has to be 10 times our sample, as it just was. The difference here is we have a new formula, and the new formula is where we take the two different parameters that we're talking about, and then we pool things together. So I'll show you how to do that in just a moment. And then we add up the two totals, N1 and the N2. So with this count of success in both samples combined means we put them together because in the formula down below here, you'll see this thing that says PC. This PC that you see here is this pooled information between the two samples. It is probably the biggest error that's made on exams, that people forget to pool. So when you do a test of significance, not confidence interval, test of significance between two proportions, you have to pool the information. I would put a star by that. Make sure you know that. That's very important for today. Okay, pooled information. I'll show you in the context of the problem. That's probably the major difference between two-sample confidence interval and test. And then in our conclusion, it's the same as always. If we don't know the significance level, we're going to assume alpha is 0.05. We see what happens with our probability. If the probability is not less than our significance level, then we fail to reject. If it is less, then we reject it. And as always, we could have a greater than, a less than, or not equal. Let's try one. So number one, are teenagers going deaf? What you say? What? In a study of 3,000 randomly selected teenagers in 1988 to 1994, 15% showed some hearing loss. In a similar study, 1,800 teenagers in 05 to 06, 19.5% showed some hearing loss. Does this data give convincing evidence that the proportion of all teens with hearing loss has increased? So, when we start out, we say in our null hypothesis that the difference between these two proportions is 0. And in our alternative hypothesis, we say that it's more than 0. And again, we get to define whatever. So since I did P1 minus P2, I could have done P 2005 minus P 1988, but that's too much writing, so now I'm going to define them so I don't have to worry about that anymore. So I'm going to say that P1 equals proportion of teens with hearing loss in 2005, and P2 will be the proportion of teens with hearing loss in 1988. So you can go about it a couple different ways. I mean, if you want to write down 2005, 1988, you go right ahead. Less writing for me is good. Then the next thing that we do is we talk about the test we're going to use in our plan part. Aaron, did you have a question?
Yeah.
All right. So next we're going to do, we'll do a two-sample Z
I mean, the significant sense.
test for, and I'm just going to write down P1 minus P2 because we've already defined it, right? If we define them, I can say that and I'm okay. Or I'm just going to say I'm okay. We have two random samples of teens, 3,000, and what was the other one? 1,800? 1,800?
Yeah.
Okay, 1,800. The two samples are independent because there are more than 30,000 teens in the US. And so now, we have to do normalness, don't we? So normalness, we should check both samples. So N1, P hat 1 has to be bigger than or equal to 10. If I do the math there, my sources say 351. If I do N1, 1 minus P hat 1 greater than or equal to 10, I get the number 1449. And then, of course, I have to do the other sample, which was sample number 2. So N2, P2 hat greater than or equal to 10. The number I get there is 450. And N2, 1 minus P2 hat has to be bigger than or equal to 10. And the number I get there is 2550. And again, I'm assuming that you guys can multiply those numbers out. If you go back and you look and you have a question, please feel free to answer this. So they're normal. Okay, so when we're doing our math, the first thing that you want to do, because there's something different about when you're doing tests of significance, the main difference is that you have this pooled proportion. So what we're going to do is we're going to talk about this pooled proportion. So one of them is the NP here, and the other one's the NP there. So in my pooled proportion, I write it like this. P hat C. I don't really know why. They must be talking about combined instead of pooled. Maybe they didn't want to write down PP for proportion pooled. I would have wrote PP myself, but whatever. So this is 351 from the formula plus 450 for the two pieces of the pooled information. Success and success, remember. And then that was out of the sample sizes of 1,800, and it doesn't matter which order you add them in, and 3,000. So this pooled proportion is approximately 0.167 to 3 decimal places. Now the reason we need that is because we're going to do the math with that pooled proportion. If you recall, our formula looked something like this from the previous page. Our Z statistic is going to be P1 hat minus P2 hat. They actually write down, believe it or not, minus 0. The reason they're writing down minus 0 is to indicate that the difference should be 0. So that's why they're putting the 0 here. Mathematically, it's not necessary. It's usually 0, that there should be no difference. But they put it there to indicate that's what it is. And then on the bottom, you're going to have the square root of. And then you have this big long thing, the pooled proportion times 1 minus that pooled proportion. No. Yeah. Is that what it said on the previous one?
Yeah.
Yeah. over the first sample plus the same thing over the second sample. So that's our formula from the previous page. And then I do the math associated with that. So the way it would look is that you're going to have your z statistic be equal to this 0.195 minus 0.150, all of that minus 0, because again there should be no difference, all over the square root of our pool proportion, which was 0.167.
Wouldn't the first one top be flipped? Because it's P1 minus P2, so it says on the page beforehand in the formula about P2 minus P1.
Did I write them down backwards?
Yeah.
No.
Yeah, that's what we did.
Well, P1 is the proportion from 2005,
That's too far.
and that's 19.5%.
Okay, just kidding. Never mind.
Is it all right?
Yep.
Okay. So 0.167 times 0.833, all over our first sample size of 1,800, plus, and again the order, because the pool proportion is not going to matter which order you write them in inside the square root, just so you know, 0.167 times 0.833 all over the 3,000 for the other sample size. And this gives us, I believe, a z statistic of 4.09. And what this means then is we're looking for the probability of our z value being more than 4.09. Now, I'm just going to tell you right now, I mean, I could get my calculator out and do the normal CDF from 4.09 to 99. But remember, when we go 2 standard deviations out, we have 2.35. When we go 3, we're at 99.7%, or in other words, 0.15 on the tail. If you go 4, this number, when you look at, I don't even know what it is on your calculator, but I'm going to say it's roughly 0. Like, I don't know how many zeros there are before you actually run into a number, but it's pretty much nothing.
I'll do it.
Do it, I want to know. All right. Okay, so our sample result, or one more extreme, would almost never occur if the true proportion difference was 0, since our p-value, which is approximately equal to 0, is less than our alpha. Did they tell us our alpha?
No.
Equal to 0.05. We reject the null hypothesis and say there is evidence of hearing loss between the teens of 1988 and 2005. You can try